Hey, AP Chemsters, this is Mrs. Vanderwalle talking about stuff from Chapter 9. Kind of go back and review really quickly lattice energy before we hit Chapter 9.10, which talks about bond energies. If you were not here on Friday, we're talking, we briefly talked about lattice energy. And if you remember what lattice energy is, it's the energy associated with the formation of the crystalline lattice of alternating cations and anions from gaseous ions. So if you look at the picture here, we have the gaseous ions, snapping together to make the crystal right here. So think of that as very exothermic, where you have that snapping going. I just clap my hands again, and then you form your crystal lattice. So notice the difference. This is your heat of formation that we learned about way back when we were talking about the standard states. I love my board. Notice how that's a solid. Notice how that's your gas. That is not lattice energy. Down here is your lattice energy. Your lattice energy is from your gaseous ions. Okay, same page. How does this occur? This is an important energy diagram. It puts together a lot of the energies that we talked about. If we start out right here with our heat of formation, this is where you start off with sodium solid and 1/2 a mole of chlorine gas. And you're going through these different steps that you'll see, going from here to here to here. There's your ionization energy, there's your endothermics. But down here is your electron affinity, where the chloride or the chlorine ion, the chlorine gas atom gains electron affinity. This is your lattice energy. Notice how greatly exothermic it is. Huge exothermic number. So that's where the lattice energy comes in. Now, if you've watched the video from Mrs. Blankenship already, that you'll see how this is working. I want to show you something else. I believe you got this was a negative, I think 788. Wasn't that what Mrs. Blankenship said? But if you look at the next page, here is lithium fluoride, and here's the lattice energy from lithium fluoride. And notice that the value is much more negative, much more exothermic than for sodium chloride. And you may wonder, why is there such a difference? Well, here's NaCl, and here's LiF. It has to go back to talk about Coulomb's law. Okay, the charge of sodium is +1, charge of chlorine is -1, charge of lithium is +1, charge of chlorine is -1. So is it the Q values that are going to really affect the size of or how exothermic the lattice energy is? No. So they both have the same Q values. It's your R value. The R here, well, which is a bigger ion, sodium or chloride? Sodium's bigger. Which is a bigger ion, the chloride or the fluoride? The chloride's bigger. So your R here is bigger. And if the R is bigger in the denominator, your E is going to be less. So that's why on the prior page that the sodium chloride lattice energy is lower than this page's lithium fluoride right here. Something else I want to show you is this idea of bond energy. We have not talked about bond energy. So if you go to page 19 in your notes, why don't you go do that now? Okay, here's page 19 in your notes, and notice that these are your average bond energies. And they talk about the FF bond energy. So here it's written as 159, but you're going to use a 1/2 a mole of the FF molecule, if you will. And so 1/2 of 159 is like 78 or something, which is awfully close to that 74 that they had listed on the other page. If you go back and look at the NaCl, and you talk about the bond energy of the chloride, here it is. Well, what's 1/2 of 243? That's going to be your, 121.5. Go back on that first page again. You're going to see that that's pretty much what they put for that diagram of NaCl. So let me pause this and go back. Yeah, so this is what I was talking about. So if you look at the bond energy from page 19, you're going to see that for 1 mole of CO2, that was your, what, 243. And if we take half of that, because you only want, right here, a half of the CO2 to get one chlorine atom, then it's going to be half of that 243, and that's where that number came from. All right, I'm going to just, I think maybe what we summarize lattice energy, make sure you understand this. What happens as the radius gets bigger, okay, your lattice energy gets smaller. What happens when you have greater charges, like what we see here? This is your +1, -1, this is your +2, -2. Notice your lattice energy gets much, much bigger. So actually your charges have a greater effect than the radius. But still, if the charges are equal, the radius then plays a part here. That's all I really want to say about lattice energy. Let's go back to what that page 19 was and talk about bond energy. Okay, it would be a really good idea if you had a calculator handy, because you're going to be definitely using it. And we're going to be talking about bond energy here. We did not have a breakball over this section, so this is going to be new stuff, especially if you're absent when we do this in class. What is going on here? So bond energy is always going to be endothermic. Think about it. If you were trying to break a stick, doesn't that require energy to break a stick apart? What if you want to try to break 2 sticks? It's going to require that much more energy. What if you put 3 sticks together? It's going to require even more energy. So what's happening here is that, let's just kind of look at some of these numbers here. Right down there, we see the chlorine single bond, chlorine double bond, and the carbon single bond, the carbon double bond, and the carbon triple bond. Notice what's happening as you increase the number of bonds. You're going to have more attraction and much, much harder to break. What else can we look at? What other trends can we look at? Well, if I just look at those two here, why do you think they both have single bonds, by the way, if you were to draw them? So chlorine has a single bond, HCl has a single bond. So why is there a difference? Why is the HCl about twice as much energy to break than the chlorine bond? Well, you might as well think about it. Pretty much in this whole unit, in the last unit, everything really revolved around attraction. Why would HCl have a greater attraction than ClCl? Don't talk about effective nuclear charge. That would work opposite for you, actually. But you can talk about shells. The H is in the first shell, the Cl is in the third shell. The H has more attraction due to its closer proximity to the nucleus, and therefore the HCl bond is more harder to break. So there's more attraction going on here. There's some more questions down below. It says observations going down a group. Well, what do you notice in general? Here's HF, HCl, HBr, HI. Look at those numbers. What's happening as you go down a group? Well, the bond energy is also going down. Again, tell me why. HI is a large molecule, therefore lower attraction, therefore it's going to be easier to break that covalent bond. Going across the period, you notice there's a little blip in those numbers. In general, what's happening is you go across the period, and you look at those numbers, they're getting, as a rule, getting bigger. I should put the S in that circle, just going up to C and O, and then the F. So you'll see that overall they're getting bigger. Again, high effective nuclear charge, so the bond energy is going to be greater. Okay, how is this going to be used? This you'll probably see on an AP exam someplace, using the average bond energies to estimate the enthalpy charge, okay, or excuse me, the enthalpy change for reaction. And your equation is summation of the bonds broken. Again, that's endothermic, right? It takes energy to break the bonds. And then plus the summation of bonds formed. Well, what's the opposite of breaking bonds? Is going to be forming bonds, and so this is going to be your X. So let me show you something. Do you remember these graphs that we showed you over and over again? These are your reactants, these are your products, this is your activation complex, this is your activation energy to get to that. What's always going to happen when you get to the activated complex? Bonds are broken. Once you have this, nebulous of, free atoms here, what's going to happen? They're going to snap together to form your products. This is your bonds form. Notice that going up the hill, always breaking bonds is your endothermic, and they snap together. This is going to be your exothermic section where you're forming your bonds. So let's check this out, how this actually works. You want to be flipping back and forth from page 9. I'm going to cross this out. I'm going to start this from scratch, okay? Let's look at this equation, and I'm going to kind of draw it out. So here's my CH4, and then I have a ClCl, and now I have CH3, Cl, and HCl. So I'm looking at all the bonds. So if I am looking at my bonds formed, I think I'm going to actually use maybe a different color pen here. So if I have bonds broken, and then bonds, let me try the pen, bonds formed. Okay, let's try this out. So what bonds are being broken? I have 1, 2, 3, 4 CH bonds. What else am I going to break? I have to break my chlorine-chlorine bond. Okay, now what? What bonds are being formed? I have 1, 2, 3 CH bonds. I have 1 CCl bond, and I have 1 HCl bond. So what we need to do is use our page 19 and go back and forth and see what these numbers are for these values. So if you look at CH on page 19, you'll see 414. You see ClCl, you'll see 243. You see the CH, once again, it's 414. Now look for CCl. It's kind of the bottom of the right or the left-hand column. I see 339. And then HCl is kind of towards the top. It's 431. Now wait a minute. We said bonds broken require energy. Those are your endothermic positive values. But what about forming bonds? They are negative. So when you use your calculator, you're going to go 4 times 414 plus 1 times 243. Now what? 3 times negative 414 plus 1 times negative 339 plus 1 times negative 431. Pause this, see what you get. Let's see what I get. Hang on. All right, what did you end up getting? Did you get a total value equals negative 113 kilojoules, negative 113 kilojoules? What does that tell you? The overall result is exothermic. Okay, let's try the, letter B right here. Reaction is exothermic when weak bonds break and stronger bonds with those snapping together is more energy released than the little bit of energy it takes to break them. The opposite is true. If you have really strong bonds, it's going to take a lot more energy to break them, and you're going to have a small snapping back together again for endothermic. So it says use the bond energies to calculate the heat reaction. Do the same thing again. Once again, Mrs. Vanderwaller's helpful hints is to draw the structures first. Okay, so if you draw the structures, plus 2, we'll move right here, and then CO2. Remember what CO2 was? It was a double bond. Okay, go ahead and I'm about running out of time here. Try this on your own and probably check. All right, I can get this in here. Another 30 seconds. Pause this, see how you do. Okay, so here, I hope you found that I made a mistake here, so I fixed it. And when you do the math, remember to get the negatives here. And you end up, when you put it all together, is a positive 170 kilojoules, and is endothermic. Okay. The one thing to make sure you know why I got 4 of these bonds, because you have 1, 2, and one water molecule with two water molecules. That's why that was a